All right. On number 10, what were our choices here? You guys are saying one group thinks it's which one?
It's 4.
It's either 4 or 6. Okay, just wait. So we got y prime equals negative t times y. That's 4. And what was 6? Negative y over t. All right. Now y is the output variable, t is the input variable. And so just to revisit this quickly, when we're trying to match the slope field with the differential equation, we look at the columns and see if it has only t, only y, or both. In this case, as you go vertically to different y values, the slopes are changing, so y must be involved. As we go horizontally to different x values, it's also changing. And so x and y, or t and y, both have to be involved. So we start looking at the ones that have both t and y. And then we do what? Plug in some points, okay? And so, for example, a good one to plug in often is 0. Is there any places where the slope is 0? And in this case, it looks like the slope is tending towards 0 right here at the y-axis. So that'd be when x is 0. So when x is 0 in this one, you get 0. When x is 0 in this one, it'll be undefined, which undefined slope means vertical, right? So that one doesn't seem to work very well. Okay? Now down here it might. It also looks like the slope is 0 down here at the x-axis, which is when y is 0. Well, when y is 0, this one would be 0, and so would this. So it seems to work there. They both seem to work there. Okay? Or you could come into a point like 1, 1. Right in here, the point 1, 1, the slope looks like it's negative something. Well, if you put a 1 in here and a 1 in here, that's negative 1. You put a 1 in both of those, that's also negative 1. So that's not a lot of help. Okay? And that might not actually help in any of them. Probably. 3, 3 up here. So up in this corner here, if you put, well, oh, yeah, I see. 3 times 3 would be negative 9. So a pretty steep negative, which is what that looks like. If you put 3 over 3, that's 1, negative 1. That's clearly not a slope of negative 1. So again, that one doesn't look too good there. Okay, so that's how we identify that. First with the columns and decide if x is in it, y is in it, or both, and then plot some points. Okay, so number 11 would be what? 8. Number 12? 9. Number 13? 10. 14?
6.
14 is the one that would be 6. Okay? All right. So that's the matching situation and how we identify the slope field. We also need to be able to draw slope fields, okay? And then the last thing that would be those number 23 and number 24, so let's talk about those. Now, if you did this really properly, 23 and 24, you probably used up a good part of your paper. I mean, I'm going through there and I'm seeing people that had 23 done in about 4 lines. Well, that would be hard to do. And actually write it out as you would want to on the quiz. Okay, now we can use our calculators to solve the equation. Okay, and as you do more of these, and somebody in the other class pointed out when they were in working at lunch yesterday, that on 23, once you did part A, then part B was pretty much the same thing. If you kind of got what you were doing in part A when you did part B, it's like more of the same. And once you get the hang of that, you could just kind of know what the A will be and what those values will be. And so I understand that. That's fine. But doing it multiple times is okay because you're going to have to do it on the quiz for sure. So it would be nice to just be able to do it in your sleep without much problem. And then to be honest, part C is pretty much the same thing. There's only, as you go through these problems, only a couple things you possibly could do. So on 23, essentially what we're talking about is Newton's law of cooling, which is this differential equation, which quite honestly you don't even need to really worry about. Rarely do we use the differential equation in the problem. In this particular problem, we have said, well, we're just going to memorize that the solution to Newton's law of cooling is this right here. Okay? And so this is what you're working with, is this equation right here. What's Y? Temperature of the object that's cooling. Little t, time, big T, surrounding temperature, air temperature, whatever the surroundings are. A, now A and K are just constants. What did you find? What does A depend on? Well, no. Big T.
Yeah.
And the starting temperature. It depends on the starting temperature and it depends on the surrounding temperature. Because what happens well, let's just start with number 23, the Boris and Natasha problem. Does anybody know where that comes from? Boris and Natasha, Rocky and Bullwinkle, those characters. That was the idea of that. Rocky Bullwinkle's the moose and the squirrel, right? And Boris and Natasha are like the Russian spies, the nemesis, right? So, I mean, that was the point of this problem. But anyway, and in this problem, Boris is the one that he doesn't care about the environment, right? So he's going to get his coffee in a styrofoam cup, environmentally destructive styrofoam, I think it said. And then Natasha was going to, yeah. So the A value depends on the starting temperature and the surrounding temperature, and then the K value depends on what? Well, like it said in the problem. Material, the insulating material that the liquid is in, or maybe also the chemical or physical properties of the whatever it is it's cooling that may affect its cooling rate. So K has to do with the cooling rate, and whatever variables would fit into that. Okay. So in this problem, we know it started at 90 degrees. So what happens then when you put 90 in for your Y? And the surroundings was 65 degrees, and so we don't know A, and then what you soon find out, if you work very many of these problems, you realize that when you put a 0 in here, it doesn't matter what K is, K times 0, you get 0, E to the 0 is 1, so what you find out is A depends solely on big T and the initial temperature 90. And so when you subtract those, you get what, 25? Did I do that right? It's 65? Yeah, I did it wrong. I was thinking of the other. I was thinking of 24. I'm sorry. I knew as soon as I wrote that wasn't right. 20. The surrounding temperature in this problem is the outside temperature because they take the coffee outside, which was negative 10. Yeah, that's right. And so then we add the 10 over there, we get 100. So A is 100 for both Boris's coffee and Natasha's, right? Because they both have the same starting temperature and they both have the same starting temperature, and they both have the same environmental or surrounding temperature. Okay, so now what's best is to rewrite your equation. Okay, so it ends up being this. All right, now in the problem we did yesterday, and I think this happens to you on number 24, right? On 24, they didn't tell you the K value, right? They gave you the starting temperature, and then they said, okay, and then 2 minutes later, the temperature is this. Yeah. Then 2 minutes later, the temperature is this. So what we would do then is we would put that temperature in for Y, and we put a 2 in for T, and we would solve for K, all right? But we don't need to do that here because they've told us the K value. So if we've got Boris's coffee, his is a K value of, I can't remember which one is which. Okay, so Boris's is negative 0.05, and Natasha's is negative 0.08. Okay, and so there's really only about 2 different. Once you get this, I mean, if these problems are really not difficult. I mean, once you make sure you memorize the law of cooling problem, there's really only one. And once you realize you plug in your initial condition to find A, which is usually the first one you find, okay, then there's really about only 2 things you can do. You're either going to find T or, like we said, K, but that's doing the same thing. Or you're going to plug a number in for T and then just figure and get the Y. And use your calculator for both of those parts. Okay? So the first question they ask is, how long does it stay above 70? Right? So what do I do? Oh, and by the way, that was supposed to. Yeah, I forgot the E. Okay. So I put a 70 in for y, because that's the temperature, and then I'm going to solve this. And this needs to be on your, if this was a test question, I would need to see this. I don't need to see all of these lines, I mean, when you're working this. I mean, if you put a 0 in and 90 and you can tell you've worked it up and you can tell that's going to make the A 100, I'm okay with that, okay, because there's no other way you would have come up with that. So that's fine, I don't need to see those lines necessarily. But I certainly need to see this equation right here, because you're now going to put that in your calculator and solve it. And so that would look like this. Okay, so that's where you would go into your calculator and do a solve. Okay, 70 equals da 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 da, and I put a t, comma t, and you would solve. And so that's 4.463 minutes later. This is Boris's coffee is down to 70 degrees. Okay, so you get, and so you don't need to show any other work than that. You can just do a solve right on your calculator. So what was it? 4.463 minutes. So that's the answer for Boris. And then you do the same thing for Natasha's, and you get 2.789. Okay? Because she doesn't want to harm the environment, so she's got it in more of a cardboard paper type cup, and that's not going to insulate nearly as well, and so it's going to drop, the temperature's going to drop much faster. Okay? And so you got that. Then the second part of part A was, what's the temperature after what, 5 minutes? So for that part, you're just going to, you don't know why, so you're just going to go -10 plus 100 e to the -0.05 times 5. You're simply going to plug a 5 in. Now here you don't have to do a solve, right? I mean, you could, I guess. You could solve that for y, but there's nothing really to solve. The y is already by itself. So you really only need to type that in like that. And you get what? 67.880. Just okay, 67.880. And for the other one, it was 57.032. Okay, so after 5 minutes, that was the temperature of the different coffees. Okay, so then you go to part B, and it says, okay, what if they would have drank it in the store? What changes? Yeah, this becomes 25, right? Which means A then becomes 65. So your equation ends up being 25 and 65 right here. So over here we end up with 25 and 65, and then you do exactly the same thing. You do exactly the same thing. The K is still -0.05 because it's still in the same cup. And so you have 70 equals, and then you have 25 plus 65, you do this, and you solve. Okay? And that came out to be, I don't know, you go through all 7 point something for his, right? Because there wasn't nearly as big a difference. It didn't cool as fast, right? Because when he took it out in the negative temperature out in the cold, but it cooled faster. But inside the store, it's not going to cool as fast. So it took 7 some minutes, and this one was what, 4 something? Yeah, 4 something minutes. And then after 5 minutes, his had only went down to like 76 degrees, and hers had went down to like 69 some degrees or something like that, right? So that just shows what the different effects these things have on there. But as far as solving them, it's as simple as just plugging in numbers and then putting it into your calculator. There's really no calculus involved in it. The only calculus is that it came from this differential equation, right? Newton's law of cooling comes from that differential equation. But once we have the solution, we just work with it by plugging numbers in and use our calculator to solve. Okay, part C then said, what K value would keep the temperature above 70 for 5 minutes? So what would that look like? 70 is equal to, and this was outside, I think they said, right? So -10 plus 100, negative, yeah, and then 5 for T. So you put it, so basically we're plugging a 5 in for T to our original equation that we had with the 100, the -10. We're putting a 5 in for T and a 70 in for the temperature. and we're just solving for k. But you just put that in your calculator just like you put this one in your calculator and you solve for t. Okay? And you solve for k, and it's like negative 0.04445. Oops, too many zeros. Negative 0.045 or 446. Yes. Yeah, I did that wrong. You're right. There's not a negative. The k is going to be negative, but there isn't a negative in your equation. So yeah, there shouldn't be. It just eats 5, and the k comes out. Okay. So, and that's it. I mean, that's really what there is to do. And so that's very much like what would happen on 24. We can just talk about that very quickly. On 24, we've got the same scenario. The coffee started 190. What were the surrounding temp? 65. So again, we don't know the A, but we do know that at time 0 it's 190. So e to the 0, of course, is 1, so that gives us a plus 65 is 190. We subtract the 65, so that's 125. There's our a. So we end up very much where we were, okay, here. And then what's, with Boris and Natasha, we knew what k value to put in, but now what do we know? 2 minutes later, the temp's 180. So now we put our 180 there, and we put our 2 in for t, and then we put that into our calculator and we solve for k. You find the k value, and then you rewrite your equation, and then you put your numbers in what they wanted. And the answer on 24 was like 30.5 something. 30.5. Okay, so what you look at. All right. So, I mean, that's pretty much it. When it comes to differential equations, slope fields, those are the things we want to be able to do. We want to be able to draw a slope field like the one worksheet. We want to be able to match the slope fields. We want to be able to sketch a curve in to a slope field with an initial condition, and we want to be able to work with Newton's law of cooling, okay, as it relates to these differential equations, okay? So that'll be one part of the test. Half the points, maybe, might be a little less than half. More than half is probably going to be on the thing we're going to talk about today with limits. Okay? All right, so let's do that. Let's get started with the idea of limits. And so you're probably going to want to start maybe a new page in your notes for this. I'll try to keep this fairly organized, and I might even be able to put this up on the website as a PDF file. It'd probably be good to have in your own notes, I'm guessing. But yes. I don't know yet. But they're generally around 30. Yeah, I think it's going to be Monday. I think we'd be close to. I think we'd be close to doing it on Friday. Is that right?
Let's do it tomorrow.
We'd be close to doing it on Friday, but I think we'll probably go Monday. All right. Oh. Okay. All right. Now, if you look on page 220 something, 221, 220, okay, the title of this section, 4.2, says more on limits, and then it talks about limits involving infinity. And so we're going to kind of, on page 221, 222, so we're going to go back and review. Matter of fact, we might even pull out the old quiz we did on limits and look at that tomorrow. But we're going to take the work we did on limits and then kind of extend it a little bit. But first we need to review, because there could be a few problems that are on there that are like the ones we did back in chapter 2. All right, so I think this would be a good time to kind of summarize everything now about limits, including what we had learned earlier. So the first thing when it comes to limits, I think that would be good to look at would be graphical. Okay, if we're going to look at limits from a graphical perspective, all right, I think that's the easiest perspective to look at limits. All right, because basically, you know, it's the intended height of the function. It's where do the cars meet. Well, that's easy to see when you have a graph. So we're going to break limits into two different types here. The type we first did the other day, or the other chapter, is limits as x approaches a, which is essentially where do the cars meet, or do the cars meet. Okay, and when I say x approaches a, I mean a number, like x approaches 2, x approaches 3. Well, what are the different situations that can happen? Well, one situation that can happen is just the easiest of all situations is you have a graph like this, and you're looking for the limit at that point right there, and does the limit exist in a graph like that at that point? Do the cars meet? Yes, it's whatever that y value is right there. Whatever that y value is, that's the limit. Okay, that's where the cars meet. And then we learned that you could have something similar to that, but you could have a hole in the graph. Right there. Does that have a limit? Yes, the cars still meet. The diner burned down, they rebuilt it somewhere else, or maybe they didn't rebuild it at all, and it's not there at all, or whatever, but the cars meet. That is the limit, right where the hole is. That y value is the limit. All right, what about one like this? What do we say there? We say the limit does not exist. Now, I didn't get really picky about this last time, but I am going to be picky about this time. We're going to say whenever our answer is does not exist, whenever our answer is the limit does not exist, we must show why. Now for these kind of limits, that means the one-sided limits. Right? On this one we would say, limit as x approaches a from the left is maybe 1, I don't know, and the limit as x approaches a from the right is 2 or whatever. But anytime, on this next quiz, when we do a limit problem, you're either going to get an answer of a number, or you're going to get an answer of does not exist, and if you get a does not exist, you need to say why. And for the ones we've learned so far, the why is look on both sides. What's the limit on the left doing? What's the limit on the right doing? You have to put that. Now, we talked about that, but I don't think I made you do that. You could just say the limit does not exist. Okay? But that's going to have to be a part of it. Okay? So just saying does not exist is not going to be enough. You have to say why. And for these kind, it's just, well, because on the left it's here. You can't just say the cars don't meet. But you have to say the limit on the left is this, the limit on the right is this. Okay? Now, the other situation we had with limits was vertical asymptotes. And those are the ones we're really going to be focusing more on now in this chapter. Because remember, this chapter said limits involving infinity. Well, vertical asymptotes involve infinity because what you have happening here at A is you have the graphs going to positive or negative infinity. Okay? Or it's possible that they're both going to positive infinity. You could have a graph that's going like this and like this. So both sides are going to positive infinity. Again, you would say the limit does not exist. Okay, on both of these. The limit does not exist. Okay? But on this one, as x approaches a from the left, you're getting positive infinity. And as x approaches a from the right, you're getting negative infinity. Right? And on this one, the limit does not exist. But the difference here is, as x approaches a from the left, you're getting infinity. And as x approaches a from the right, you're also getting infinity. So some people would say on that bottom right one, some people would say the limit there is infinity. Now technically that still means it does not exist. Because infinity is not a number, right? Infinity is not a number. And a limit is the number where the cars meet. The cars still don't meet there. They're both going to positive infinity, but they don't meet. So technically the limit does not exist, but some people allow you to go ahead and say, hey, the limit is infinity. So if you did say that, that'd be fine, but okay, in that particular case. But it wouldn't be okay on the one on the left, because they're not both going to infinity. One's positive infinity, one's negative. Okay? So, does not exist in two different situations here. We got the limit does not exist, but in both cases, the reason why it doesn't exist is because the limit from the left and the limit from the right are not meeting at a number. If they do, then that's a limit. All right. Now, for the new thing that we're going to talk about today, we're going to talk about limits as x. This is still graphical now that I'm talking about here. So this would still be under the heading of graphical limits. We're going to talk about the limit as x approaches infinity. The limit as x approaches infinity. And for this, we're going to watch another one of our little videos. Where's my phone? Oh, oops. Did it start already?
Divided by the quantity x minus 3. Now, if you plug in 3 to this, in this section, we'll delve into the mysterious and ancient relationship that exists between limits and infinity. As you calculate various values of f and evaluate different functions, you can come across some bizarre things. For example, take a look at this function. F of x equals the fraction 2x plus 1 divided by the quantity x minus 3. Now, if you plug in 3 to this, you're going to get 7 divided by 0. Now, I know we've seen 0 divided by 0 in a lot of previous examples, but we've never seen a non-zero number divided by 0. Well, that's bizarre, I know, and it indicates something important. In fact, whenever you substitute a number into a function and get a non-zero number divided by 0, it indicates the presence of a vertical asymptote. And this holds true for this function. Let's take a look at the graph of f at x equals 3. Well, remember, an asymptote is a line which a function cannot reach. Here we have an asymptote at x equals 3, because when we plugged 3 into f, we got a constant divided by 0. Now, by examining the graph of f, we can see that the limits as x approaches 3 from the left and right are different. As you approach 3 from the right, f gets infinitely large, so we can say that the limit as x approaches 3 from the right of f of x is infinity. However, as you approach 3 from the left, f of x gets infinitely negative, so we say that the limit as x approaches 3 from the left of f of x is negative infinity.
Okay, now, yeah, I forgot, I could have shown that just a minute earlier, but okay, so what they were referencing is this one down here that we were talking about. And here in a minute, we're going to look at these limits, not graphically, but algebraically. And we're going to talk about how do we know if it's going to be one of these vertical asymptote problems. Well, that's what they just got to say. If you get 7 over 0 or 5 over 0, and we had talked about this last time. If you get that, that means there's going to be vertical asymptote. Well, you just saw what they said. The cars are going, one's going to positive infinity, one's going to negative infinity. Okay? And that's how we'll do it. So that's the graphical perspective. All right? So let's look at the next part. The next part, I think, then, gets into what we're talking about here.
Vertical asymptotes aren't the only asymptotes which relate to infinity. Horizontal asymptotes do as well, just in a slightly different way. To see this, let's look at the graph of f again. Now, as x gets infinitely large, or as we go along the x-axis, note that the graph of f is bending slowly downwards towards a height of 2. Now, if a graphical argument is not enough for you, take a look at this chart based on the function values of f. As x gets larger, f gets closer to 2. Now, mathematically, this means that the limit as x approaches infinity of f equals 2. By the way, the limit as x approaches negative infinity of f also equals 2. As we travel left along the x-axis. The function approaches the same height. When I was explaining the last example, I said that x was getting infinitely large, and we translated that mathematically. In this section, we'll delve into the mysterious and ancient relationship that exists between limits and infinity. As you calculate various values of f and evaluate different functions, you can
We'll just let that run. All right, so horizontal asymptote. So when you say the limit as x approaches infinity, now this is different. Before it was x approaches a number. Infinity is not a number. So what you notice is x approaching infinity means that x gets really big. Well, on a graph, when x gets really big, we're talking about way out to the right. Or if x approaches negative infinity, we're talking about way out to the left. Well, what's a graph doing out there? Well, one of the things it could be doing is approaching a horizontal asymptote. So when you have a problem like this, you're basically you're really thinking about horizontal asymptotes. Now, it might not have a horizontal asymptote. I mean, you might have as simple a problem, and don't write this down, but you might have as simple of a problem as this right here. What's the limit of x squared as x approaches infinity? It's infinity, right? Now, let's back up a minute. If you're talking about as x approaches infinity, are you going to have cars meeting? No, because there's not two sides, right? You can't get on the other side of infinity, right? What you have is one car going out to infinity. So what y value is it approaching? So we're not talking about cars meeting here for limit exists or does not exist, right? The cars don't meet, the limit doesn't exist in the other ones. But in these, the limit exists if the car, as it goes out to infinity, is approaching some y value, horizontal asymptote. If it's not, if it's just going up, a parabola just goes up and up and up, right? That car would just be going up forever. Technically, that is the limit does not exist because it's not approaching a number. The car is not approaching a number. It's just going up to infinity. But it is okay, that's like the one I was just talking about a minute ago. It would be okay here to say, in this case, that the limit is infinity. It would also be okay to say the limit does not exist, okay? But remember, we said if you say the limit does not exist, you have to say why. Well, in this case, the why is because it's going to infinity. So if you say does not exist, you should put both of those things. If you just put infinity, that's okay. And we'll just agree that we understand that if we say infinity, we're saying, hey, it doesn't go to a number. It goes to infinity. Okay, so the limit does not exist. So it's okay to put both, or it's okay to just put infinity. Okay, but you never, from this point on, we never just say does not exist without some other explanation of why. On the other ones, it's because the cars don't meet. So we look at the left, we look at the right. On these, it does not exist because it's going to infinity. Now, in a minute, we'll talk about plugging in, right? Remember, we talked about direct substitution. One of the things you always do if you're doing the limit as x approaches 2, you just plug in a 2. Well, we can talk about plugging in an infinity. And technically, that's not true because infinity is not a number. You don't plug in infinity, but you could think of it that way. So we could say, well, you do infinity, that'd be like infinity squared. Well, that's infinity, right? A billion squared is a great big number. And a trillion squared is even bigger, and so forth and so on. So as x gets really, really big, x squared is going to get big, 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 even bigger. So it's going to go to infinity. Okay? Now, graphically, and that's what I wanted to, this is the part you would maybe put in your notes here. Okay, so graphically, we're talking about situations that might look like this. So a graph that kind of comes down and approaches this horizontal asymptote like this, and like the example they gave, and then approaches from this side, right? That would be one possibility. Another possibility that can happen is you can get a graph that comes down like this and then bounces around, and then eventually, I mean, it just keeps bouncing. Remember, you can cross a horizontal asymptote, and it just keeps bouncing back and forth, but it's getting closer and closer and closer to zero, or whatever the horizontal asymptote is. But it's perfectly legal to cross, okay? So here, as x approaches infinity, this limit would be 0. As you go to negative infinity, this limit would be infinity, or does not exist, because it's going to infinity, right? So it's possible when you go to positive infinity, you have a limit, in this case 0. and going to negative infinity, it does not. Okay? You can also have one that's got two different limits. You can have two different horizontal asymptotes, right? You can have a graph that comes down and does this on this side, and on this side, comes up like so. So as x approaches infinity, way out here, it's approaching this value, say 2 or something, and way out here at negative infinity, it's approaching negative 2. Okay? Okay. So graphically, that's pretty easy, but most of, probably all of the limit problems we do on this quiz are not going to have graphs, and we're not going to use our calculator. They're going to be algebraically, doing limits. Okay, so that's the next thing we want to talk about. All right, so hang on a second, let me make sure it finishes that one. Okay, so let's talk about algebraically now. How do we algebraically solve these limits? All right, so let's review, first of all, the ones that we did earlier in the year. So let's do this possible example. The limit, let's start here with limits as x approaches a. Okay, these are the ones that we did before. And one of them we're going to do a little extension on, a little different than we did before. So the first one, the most simple one, is this. Limit as x approaches 2, x squared minus 1. What do you do to do that limit right there? You substitute, right? You put a 2 in for x. 2 squared is 4, 4 minus 1 is 3, that is your answer. Okay, so the first thing that can happen is you just get a number answer, and that is your limit. Don't forget, 0 is just a number. If you had this problem here, limit as x approaches 1, of x minus 1 over x plus 2, again, direct substitution, you plug in a 1, what do you get? 0 over 3, but that's just 0, which is just a number. It's fine to have 0 on top over 3. There's no problem there. That's just 0. So one thing that can happen is you get just a number. Okay? And that's what we would hope would happen, is that we'll get a number answer. That's the limit. The limit exists. That's what it approaches. Okay? So those are the simplest of the examples. Okay? Here's the other one that another one that we did. Limit as x approaches 2, x squared minus 4 over x minus 2. And we try to plug in our 2, and what happens? Well, not only do you divide by 0, but you get, no, not a vertical asymptote. You get 0 over 0. Now, we will talk more about this tomorrow, but this is a really special case. Now, what we did in the past on this one is we said what? If you get 0 over 0, what do? Keep going, right? Keep going. If you get 0 over 0, the term we used was indeterminate. You cannot determine whether there's a limit or not. We're going to talk a lot more about that terminology tomorrow. But we get indeterminate. That means keep going. Now, the keep going for us algebraically, conjugate method, get a common denominator, factor. That was the thing we did on the last quiz. We had all this practice on that algebra stuff we did. We're not going to get that much into the algebra part of it on this one. There probably won't be any conjugate ones or anything like that, so we have to worry about that. There might be a factoring one. That should be pretty easy. So we get 0, 0 means keep going. So what we do is we factor the top, x plus 2, x minus 2. We factor the bottom, which I guess it doesn't factor, but the x minus 2's cancel, which of course is what was causing the 0 over 0. So what do we do next? Now we plug in our 2. 2 plus 2 is 4, and now that's our answer. So that is our limit. And if you remember, this was a graph with a hole in it. We talked about that. That's what 0 over 0 typically means, is that the graph has a hole in it. Well, the cars are still meeting. So the cars still meet there, so it's not a problem. That is the limit. But when we got 0, 0, we had to keep going, do some algebra to get it. All right? Now, the one that they're going to talk about here in the video is going to be one like this. Limit as x approaches. Shoot. I think it's 2x. You guys remember the one they did there? It's 2x plus 1 over x minus 3, I think. As x approaches 3. I think that's what they did. Now on that one, you plug in a 3, and what do you get? 7 over 0. That is the vertical asymptote. When you get a non-zero number, like 7 or -2 or whatever, over 0, that's a vertical asymptote. Now let me say again, and this, it wasn't as important when we did this in chapter 2, but this is going to be really important to understand this. The reason this is a vertical asymptote is you don't really have 7 divided by 0 here. What you have is as x gets close to 3, you have the top getting close to 7 and the bottom getting close to 0. Well, what happens if you take a number close to 7 and divide it by something close to 0? Now, how close? Well, real close. Well, what's close to 0? Well, how about like 1/1,000,000th? What if you take 7 divided by 1/1,000,000th? 7 million. A big number. And the smaller the bottom gets, what happens to the fraction? Gets bigger. So as x gets closer to 3, the bottom gets closer and closer to 0, so the bottom gets really small, and if you take a non-zero top number and divide by a really small bottom number, the fraction itself gets bigger towards infinity. That's why a number over 0 is a vertical asymptote situation. Okay? Because that involves infinity. All we have to do is go back a couple pages, and we're looking at this kind of scenario right here. Yes?
How do we know if we have a vertical or horizontal?
Okay? Great question. And here it is. Horizontal asymptote is what happens as x gets really, really big. As x gets really, really big. Okay? The input gets really, really big. So we're talking about as we go way out here on the graph. That's a horizontal asymptote, way out there. A vertical asymptote is when the y values are getting really, really big. As x approaches a number, this vertical line. So vertical asymptotes are always going to be when you have a problem like this, as x approaches 3 or as x approaches 2. A horizontal asymptote is always as x approaches infinity. And that is the difference, whether we're going that way or the up and down. Okay? And that's why I'm trying to organize this all here a little bit so we can kind of make sense of it. So when I get 7 over 0, that tells me I'm going to have a vertical asymptote. Now, here's what we did. This is as far as we got in chapter 2 when we did this. At this point, I told you guys, if you get 7 over 0, you just write does not exist. That's what I told you last time. Just see does not exist and just stop right there. But now, what have I said today? That's not good enough. You have to show why. Well, now, remember, what are we doing here? We're talking about as x approaches 3, right? So we have a left and a right side as we come into 3, right? What we're having is the cars aren't meeting. One's going like this and like this, or they're both going like this, or they're both going like this. But we do have a situation where are the cars meeting here? Because we're talking about as x approaches 3. Okay? So let's look at it graphically on this video just real quick, and then we'll talk about how we're going to work it.
Was getting infinitely large, and we translated that mathematically as the limit as x approaches infinity. Now this type of limit is called a limit at infinity. If this limit exists for a function, then that function possesses a horizontal asymptote at the height given by the limit.
Here they're talking about the horizontal asymptotes.
But it's very simple in practice. Limits at infinity are very easy to calculate. All you have to do is compare the degrees in the...
That's not what I
In this section, we'll delve
Dang
into the
it.
mysterious and ancient relationship that exists between limits and...
Oh, that's a good basketball. All right. All right. All right.
If you pull that up.
And then, yeah, oh yeah, maybe you guys
Yeah, we need
could
some
work,
strategy.
need a play or something. Maybe,
We need a coach.
maybe we could
We
work
need
on a
help.
play
We
or
need a lot of
something.
help.
All right, there might be an NSA
Squeeze the
rule
Leah's
inside
shirt.
or something. You think I get Bill Small? The shirt that would fit me? I know, I've
You
seen
can
it.
squeeze into Leah's.
All right. Okay, so let's forget about those videos. What they would do here is they would just show a graph of the cars. Well, I think they were did on that one, showing the car, one car going up, one car going down, and they're not meeting. Okay, here's how I want this to look. Oh, whoops, I shouldn't have closed that. Okay, so here's how I want this. Here's how your work's going to look. Here's how you're going to show Y. Okay, so it says does not exist. Okay, we got to show Y. Show why the cars don't meet. Well, here's why. Because as x approaches 3 from the left, we're going to get one thing. So we're going to do I'll go ahead and write it out. You wouldn't have to write all this out. But we're going to do the limit as x approaches 3 from the left. And we're going to do the limit as x approaches 3 from the right. Okay? And what we did, actually what you guys did on the last quiz on one like this is you put in your calculator. And we're not going to do that again. Okay, but we put in our calculator and looked at the table. So you looked at the left side table and the right side table. And if the numbers were getting really big, that was infinity. Okay, and I didn't make you write it out. Well, this time we're going to do it without a calculator. We're just going to calculate it by hand. But actually, the calculation is very easy. All right, so as x approaches 3 from the left, well, what's a number that's close to 3 from the left? Even closer. Even closer. 2.999, whatever. I don't care how many nines you put in there, but basically we're talking about approaching 3 from the left. We're talking about 2.999. So what I want to do, we can't plug a 3 in. We already did that. We plugged a 3 in and we got 7 over 0. Right? You can't divide by 0, so that didn't do me any good. So I need to look at the left and the right. So I'm going to plug in a 2.999. So what's 2 times 2 point? Well, you know what? I don't even care on the top, really. I can go ahead and plug a 3 in the top. Why? Well, we'll see in a minute. But because it's not giving me a 0. See, the 0 is the problem, right? Not the 7. So if I plug a 3 in here, we just say we get 7. Okay? Actually, it'd be a little bit less than 7, right? Because it's a little less than 3. So, okay, but I don't really care about that. But what happens on the bottom when I put 2.999 in? I get a negative 0.000, and I don't even care how many zeros you have. Matter of fact, I don't even care if you write that. If you just want to write small negative, that's good enough. But the key is it's negative, right? We know it's getting small. That's why the 0 was there when we plugged in a 3. It was 0. So if I put in a 2.999 minus 3, that's a really small negative. What happens if you take 7 divided by a really small negative? You get a really big negative. So what we just found there is that on the left of 3, this is going towards negative infinity. And then we do the same thing for the right of 3. The right of 3 would be like 3.0001. Well, what happens if we plug 3.001 into this? We basically get 7 on top, essentially. Something really close to 7. And on the bottom, we get what? Small positive. I don't care if you put the 0.001, just put small positive. Right? You get 7 divided by a small positive. It's a large positive. So what we just did there is showed why the limit does not exist. Because the car on the left is going to negative infinity, the car on the right is going to positive infinity. They're not meeting, and so therefore the limit does not exist. So that's what I mean by whenever you say does not exist, you need to show why. Okay? So you get a number divided by 0, that's undefined, limit does not exist. But go ahead and check the left and the right. All right? So that, really the red part there is the only thing that's new or different from what we did in chapter 2. I mean, the rest of this is just stuff we did before. Okay, indeterminate, if you get 0 over 0, it means keep going. If you can plug in and just get a number, that's what you should do. And if you get a number over 0, it does not exist, but check the left and check the right. Last thing. Let's look what we did here. Okay, graphically we said, what about as x approaches a? Well, that's to do the cars meet. Might be a hole, that's like the 0 over 0 situation. If the cars don't meet, we gotta say why. On the left it was here, the right it was here. Left, this one went up there, right, that one went down there. So these pictures are like the one we just did, okay? So if I jump ahead, here's the same situation, but algebraic, all right? So now what I wanna do is look at these new ones here, okay? What about this horizontal asymptote situation? Limit as x goes to infinity. Well, if I have a picture, that's easy. I mean, if I give you one of these pictures, you can certainly tell as x goes to infinity where it's going. Okay, but what about without a calculator? What about algebraically? How are we going to do these? Okay. Oops. All right. So, last thing. And this is mostly what your homework questions are like. The homework is fairly short today. We're going to get into it more tomorrow, but just to give you a taste of it here a little bit. In fact, I think somebody in your class has been 6 minutes. Literally. Yeah, literally. Okay. But there's more to it than that. I mean, some of them got done pretty quick. I'm not sure thought very much about what was going on. And so, if there'll be more to it, obviously more. But here's the last part of it. How do we do a problem where we want to do x getting really large? We'll just start with that same one they used a little bit ago. Now the difference here is, and some of you aren't going to notice it. You're going to be confused by that a little bit, and so you got to really be careful that the difference between this one and the one we just did is what? As x approaches infinity. The one we just did was as x approaches 3. Well, when x approaches 3, what do? You plug in a 3. Well, what suppose we should do if it says x approaches infinity? Sort of, yeah. Plug in infinity. But remember, I said infinity's not a number. Technically, you don't plug in infinity, but you can plug in a billion or a trillion or something really big. Now, compared to infinity, a billion really isn't very big, right? But you'll get the idea, okay? So, actually, just think about that one a minute, okay? Just to yourself. Just think about plugging in infinity or plugging in a billion. What would that fraction be? Okay, 2 infinities over 1 infinity. Joe, you said about 2 to 1. What's that mean? What's that mean the answer would be? Think the answer would be 2? About, you keep saying about, right? Well, but isn't that what limits are? It's approaching that, right? It doesn't ever actually equal. And when we say the limit, the cars meet at the diner, technically they never actually get there, right? I mean, it's just as x is getting close to, in the other example, 3, they're getting closer to there, but they don't actually get there. So what you're saying is this is about 2 to 1, which is about 2, and that would be the limit. And actually, that is the answer. Now, for those of you that are not sure where they're coming out of that, let's just put in a billion. So what do you get on top? 2 billion and 1. Now think about that a minute, right? If I gave you $2 billion, or if I was standing here and I had $2 billion in my pocket, right? And yeah, well, 2 $1 billion bills. Okay, and so I've got $2 billion in my pocket, and there's a dollar bill. I'm walking along, and there's a dollar bill on the ground. I'm not even going to pick it up. I mean, I'm kind of lazy anyway. But it's not even going to be worth my time to pick that up, right? What's the bottom? So essentially what that means, here's what that means, okay? If I could get the video to go to the right one, or if I could remember which part was which, the video would say this, that you just ignore the 1, okay? Now, I don't want you memorizing, oh, God, how do I remember if I should ignore the 1? I want you to understand it and think about it. I want you to look at this problem and say, okay, x is getting really big, like a billion. Well, 2 billion plus 1 is basically just 2 billion. The 1 doesn't matter. So the top is essentially 2x. The plus 1 is insignificant, and the bigger x gets, the more insignificant the 1 is, right? What about the bottom? 1 billion minus 3. 999 million, 900, who cares? It's basically a billion, right? Same thing. I got $1 billion in my hand and $3 bills blow away, right? I'm not chasing. Some people, actually, that's probably why I have $1 billion, is because I care about every little dollar. I'm such a cheapskate. But the bottom is essentially x. The minus 3 doesn't count when x gets very large. Now, what I typically say on these problems, when x is going to infinity, now remember, that's only on x goes to infinity, not these other ones we were doing. When x gets really big, the high powers dominate in the problem. The high values dominate. So in other words, the plus 1 and the minus 3 don't matter. Now, what's 2x divided by x? That's where you guys were saying 2 to 1, right? That reduces to 2. That is the limit. Because this would essentially, as x gets bigger and bigger, this fraction would essentially be becoming 2. Now, the trick to these is all the different possibilities of things that can happen. And I'll try to run through many of them with you here as you see them, and then you will see them again in your home. Okay, so that's one example. All right? Now, another example, limit as x goes to infinity, is, let's say we had 3x squared minus 2x and 1 plus x squared. Okay? What do you think on that? High powers dominate. Not only does the 1 not matter when it's compared to 2 billion, but 3 billion squared minus 2 billion. 2 billion doesn't even amount to anything when compared to 1 billion squared. I mean, it's hard to imagine 1 billion not really mattering, but if you think about it, here would be 1 billion. I probably should use, yeah, that's fine. There's 1 billion, 9 zeros, right? What's 1 billion squared? 18 zeros, 9 more decimal places. So if you had, I don't even know what's 1 billion squared, what is that? Billion, trillion, quadrillion, quintillion? Would that be a quintillion? No, it'd be one more after that. Sextillion. Septillion, is it septillion? Whatever. It's got 18. But if I had $1 billion squared dollars and somebody gave me then $1 billion to add to that, basically I would have that many billion squares now, right? Because it's 9 decimal places different. It would be the same proportionally as if you had $1 billion and somebody gave you 1, right? 9 decimal places different. 1 billion times as much. So how much difference is there, whatever billion squared is, between 1 billion squared and 1.0001 billion squared, right? Hardly anything. So as hard as it is to imagine, and infinity type problems do get kind of interesting to imagine. I've got a couple of examples we'll talk about tomorrow that really make you think. But literally, this does not matter. And this does not matter. So it becomes this, which is 3. Okay? Now, all right, now we can go a little quicker with it. So on the next one here, let's do x squared plus 7 over 2x minus 1. What about this one? This basically becomes x squared over, I mean, we can't just ignore the whole bottom, right? When I say high powers dominate, I guess what I really mean is a high power on the top and a high power on the bottom, right? So what's x squared over 2x? x over 2, right? Now, as again, you can't forget, as x is getting really big, what is this? No, that's not 1/2, which is what? Infinity. Half of infinity is infinity. Now again, that seems weird, but infinity is not a number. You can't treat it like a regular number. What you're saying is a really big number divided by 2 is still a really big number. And the bigger that number gets when you divide by 2, it's still a bigger number, still growing. So as x gets bigger and bigger and bigger, x divided by 2 is getting bigger and bigger and bigger. So it's infinity. Now, I don't think you would have had to do that algebra you guys just did there. I think you could have looked at it and said, well, wait a minute. The top, as x gets really big, what's happening at the top? What? Matter of fact, let's back up a minute. Let's back up a minute on all these problems. As x gets really big, what's happening at the top? Getting really big. What's happening at the bottom? Getting really big. Now, remember when we had 0 over 0 earlier? All of these problems, we could say, are infinity over infinity problems. Now, that's something we're going to talk more about tomorrow. All of these problems are basically infinity over infinity. Now, you might think that that's 1. Well, we've just shown it's not, right? It's not 1. In this case, it was 2. In this case, it was 3. Well, why? Well, this one's going to infinity and this one's going to infinity, but why is it not 1 if they're both going to infinity?
Top one has a-
This one's going to infinity twice as fast as the bottom. So when you get into these infinity problems, it is not, and it's not only what's getting big, but it's what's getting big faster. It's the rate. It's the rate that they're getting big. And guess what? Those problems with 0 over 0 basically meant the top and bottom both getting small. It's the rate that they're both getting small. Tomorrow we'll figure out how the derivative is involved in that. Remember, I said everything in chapter 4 somehow has something to do with derivative. We haven't talked about derivative at all in any of these problems. Okay? It has to do with the rate. So every one of these is infinity over infinity. The big top and bottom both get big. This is getting big twice as fast. This is getting big 3 times as fast. So the answer is 2, answer is 3. What about this one? Top's getting big, bottom's getting big, right? But what can you tell me about the top as far as how fast it's getting big? Way, way faster. That's not very technical, but right? Because this is x squared compared to x. So I think if you really understand what's happening here as we get through the next couple days, you would look at one like this and go, oh, wow. Yeah, top's getting, as x gets really big, the top's getting big and much bigger, much faster than the bottom. So if you have a fraction where the top's getting bigger and bigger and bigger, it's going to infinity. Okay? Now let's reverse that. Okay? Let's make it 2x minus 1 on the top, and let's make it x squared plus 7 on the bottom. What's that going to be? Well, we could go through our same thought process we did on this one. We could say high powers dominate, right? So on top, it's going to be 2x. On the bottom, it's going to be x squared, which is 2 over x. So now as x gets really big, this is 2 divided by a really big number. What's 2 divided by a really big number? Really small number, right? 2 divided by a billion. Infinitely small, which means infinitely small, in other words, getting close to 0, right? Getting close to 0. Be 0.00000 something. Okay, now, all right, now I don't sense that we've just got this nailed yet here, okay? Now, so think about this. Now, on the video, they said, well, you just look at the powers. If they have equal powers, it's this. If the power top's bigger. I don't want to do that because not all our problems are just going to have powers in them. They're going to be signs or e to the x's, stuff like that. We'll do a couple quick examples here. But what I want you to see when you look at one of these problems, you say, okay, I'm doing a problem as x goes to infinity. That's a horizontal asymptote kind of thing. As x gets really big, what's this graph approaching? Or is it approaching anything? Maybe it's going up to infinity, right? Maybe it's going just like x squared, like a parabola. It's just going out of sight. So what I do is I say, okay, x is getting really big. What's happening? Well, if it's a fraction, I say, what's happening at the top? What's happening at the bottom? Well, they're both getting big. Well, a high power will dominate. So I go through it. Okay, this is 2. That would be a horizontal asymptote. So that's approaching 2. This one's approaching 3. Okay? This one, the top is getting big, so is the bottom, but the top's getting big much faster. If the top of a fraction gets really big, then the whole fraction gets big. So this is one of those that's just going out of sight. Okay? We go way to the right on the graph, it's just going way, way up. On this one, the bottom's getting big, faster compared to the top. And when that happens, it goes to 0. Okay, just like we said, if you have a fraction and the bottom gets little, the whole fraction gets big. Well, if you have a fraction and the bottom gets big, the whole fraction gets little. Okay, they work in reverse proportion.
So the third one wouldn't have an asymptote,
So this one right here, there would not be a horizontal asymptote because it didn't come out a number. That would be one like a parabola where it just goes out of sight. Okay, but on these, they would all be horizontal asymptotes. This one would come down and hit the x-axis. Okay? All right. What about one that doesn't have powers? These are the ones that really make you kind of think about it. Okay? And actually there's several of these on your homework. Okay, what about that one right there? You can't just do something with powers, right? And there's no algebra that we could do to simplify that, right? We can't talk about high powers dominate or anything like that. So this is where you just have to think your way through it. Okay, go ahead.
Well, what if the sign is something less than 1?
Yeah, or 1.
It could be 1,
Because
or less than 1, or
0.
0, or -1. It's something between -1 and 1. Very good. Now remember, we're talking about as x gets really big. So we're talking about way, way out, whatever this graph looks like, way, way out here, a billion, a trillion, whatever. What's the sine graph do? Just keeps doing this, right? Just keeps going up and down, up and down, up and down. So what we're looking at here are values between 1 and -1. Okay, right. Okay, so what? Keep going.
well, the bottom is going to keep getting bigger.
And the bottom's going to get huge. So what you have are numbers on top that are alternating from -1 to 1 in between there, divided by a really, really big number. It's going to go to 0. Now, it's going to alternate from negative to positive, right? Because when sign is negative, you're going to have negative divided by a really big positive. And that's going to be 0, but it'll be or close to 0. It'll be really small, but it'll be negative. But then when sign turns and goes positive, you'll have a positive number divided by a really big number, and that'll be a really small positive number. So what you have is one of these graphs I've been talking about here, where you're going to have a graph where way out here is just going to be doing this. It's just going to be alternating from positive to negative, but it's getting closer and closer to 0. It's still approaching that horizontal asymptote of 0. So the only way that you come is to just to reason your way through it. Okay? Just like you just did. All right? Here's another one. Think about that one a minute. Anybody think they got something? Right?
I think it's going to be 0.
Okay. Anybody else? Nick? Okay. Those are kind of the opposite extreme. Infinity? Ryan, why do you think 0? Sam, do you think 0?
Because the bottom is going to get really big, like a billion squared.
Right.
The top isn't going to get quite as big, like 2 to the billion. And that's not as quite as big as a billion squared.
Okay. Did he convince you? What?
Well, if x is going to be greater than 2 or less than -2, then
Say that again now.
Well, if you're just thinking with positives, if the x is going to be greater than 2, then the bottom's going to be larger than the top. But if, like 0 to 2, it's going to the top's going to be larger than the bottom.
But you're right. We're saying as x goes to infinity, so we're talking about way out here. We're
So it's
talking
going to
about
be
way
a very
out here.
large bottom.
Yeah, I don't care what happens at 1 or 2 or 3. I'm about a billion and farther.
But 2 are larger.
Nick, what do you think?
I think that Brian puts up a good case, but if I had ever seen 2 to the billion, or
Well, that's just it. I mean, to me, you guys, Zach, Steve, what do you think?
2 to the billion is a lot larger than a billion.
So-
Yeah, it's
So
still-
I think you guys are making the same argument. The question is, what's bigger, 2 to the billionth or a billion squared?
2 to the this gets an overflow error on 2 to the 7.
Yeah. You ever heard that thing about a grain or a penny a day doubled? Because that's really what this is, right? This is 2 to the second, 2 to the third, 2 to the fourth. That'd be 2, 4, 8, 16, 32, 64, right? And if you did that for a month, how much money you'd have? Well, now remember, that's only 2 to the 30th, right? If you doubled for a month, that'd be 2 to the 30th. Well, it's something like 2 million or something compared to 30 squared, which is what, 900? I mean, really, by the time x is 30, 2 to the x is already bigger than x squared. So 2 to the billionth, you're right, 2 to the billionth is astronomically larger than a billion squared. It's amazing, actually. And this is a really important lesson right here, just this problem alone. Exponential functions, any exponential function, well, unless the base is less than 1, like 1/2, then you get exponential decay and it gets smaller, right? But any base larger than 1 raised to the x will always outgrow anything to a power. And that includes if this was x to the billionth or x to the trillionth. If this was x to the trillionth power, this will still eventually outpace it. Okay? I don't know when, but it would be way out there. But eventually, this exponential will always outpace a power function, no matter what the power is. All right? There's a question that was on the AP test one year, and I wouldn't doubt it's on it every year, on the multiple choice part, where essentially the question comes down to this. It would look different years, but you'd have two functions like this, and it would essentially ask something like how many intersection points do they have, and it'd be on the calculator part, right? And it would ask about how many times they intersect. And so when you graph them, it looks like this. So what most students do is they grab their calculators, right? And they graph them, and they graph x squared. And then they graph 2 to the x, and it comes through and it goes like this, right? And most people would set kind of a standard viewing window, right? And of course, what does everybody put for the answer? 2. What is the answer? There's 3. Because 2 to the x eventually is going to grow and go practically straight up. It's going to grow so fast. And the parabola is just going to keep kind of going out like this. That eventually this thing, when it turns back, they will cross again. But there's no way you would ever put your window on your calculator big enough to see it. You would have to be able to reason through and know it. Okay? And of course, 2 would be one of the answers. It'd be a multiple choice question, right? And 2 would be one of the answers, and everybody would put 2. Okay? And that's essentially what they're getting at. Understanding that exponential growth always will outpace a power. So anyway, what do we think the answer is then? Infinity. Now, if I reverse those, it would be 0. Okay? So those are the kinds of questions where there isn't really an algebraic thing to think about, but it's more of a reason it out with what we're talking about. Okay? All right. So, your homework. Now, I did make a little bit of a mistake on the homework. I apologize. I don't know what happened, but day 1, 4.2 says 9 through 21 odd. That is supposed to say 9 through 21 all. And even with that, like I said, it still doesn't take very long. They're just these limit problems like we were just talking about. And most of them are with infinity. And there's another one. Call it 21.5 if you want. And I'll just write it right up here. All right, so 9 through 21 and this problem here. And you don't, somebody asked their class, do we have to write out the problem or anything? Do we just write the answer? And yeah, you can just write out the answer. Because oftentimes that's all you do. You just have to reason it through. Because most of them are infinity type limits. Oh, Matt, that wasn't a late slip, was it? That was an excused slip. Okay.